Before I start today, I'm going to give you a little bit of a history lesson. I like to do this, as you probably already gathered. In this particular case, history is a very important thing in the theory that we're going to discuss today. Alright? The person that we're going to be focusing on is a guy called Michael Faraday. Now, Michael Faraday, many people have heard of, a lot of people haven't heard of, but he was probably one of the most important people in the history of physics, and yet compared to someone like Albert Einstein, he's probably nowhere near as famous, but I would argue that he was much more important to your everyday life than Albert Einstein's work was. The work that Michael Faraday did was absolutely essential. Alright, so we will see that with Michael Faraday's theory, we now take for granted mass-produced electricity. We take for granted that when we flip the switch, we're going to get mass-produced power. That's something that we don't even ask questions about anymore. A little bit like turning a tap on and getting water, you know. We just owe it to him, really, and his ideas that we have this today. Just a little bit about him. Very interesting character. He was born very, very poor, into a very poor family, and he was so poor he could not study at college. He didn't have the money, right? And in those days, if you didn't have the money, well, you couldn't go to university. There was just no other way, all right? But he was obviously a very brilliant person. He got a job as a bookbinder. So his job was putting the front covers on books, okay? He did that for a living. But at the same time, he had a really big interest in science. Anything scientific, he was fascinated by it. And at the time, there was a very famous chemist called Humphrey Davy, who was probably one of the most famous scientists of his day. And Michael Faraday would go along and listen to his lectures. And he wrote down everything he said, just like you should be writing down everything I'm saying right now, right? Okay, he would sit there and he would write down all these detailed notes, and the story goes that at the end of the lecture, when Humphrey Davy had done about 10 lectures, he came up to him and he said, "Sir, you're a big hero of mine. I've taken all these lecture notes for you and I've bound them in this beautiful book, and here it is as a gift. Please give me a job." Okay, and apparently Humphrey Davy was sort of impressed by that, and he gave him a job, and the job he gave him was cleaning out all of the beakers in the laboratory. That's the job he gave him. Not a very good job, but at least he got close to one of his heroes. And then over the next few years, Faraday did all these amazing experiments just on his own. And eventually, in 1831, he discovered the principle behind how to turn magnetism into electricity. So really, we owe to him this idea that we can turn magnetism into electricity. Have a think about last week's lesson. We were talking more about the opposite process. Have a think about an electric motor. We talked about electric motors. What do electric motors do? We put electricity into them, we get movement or motion out of them. Well, Faraday discovered that the opposite works as well. You can actually get electricity from magnetism. And this is a much more important discovery. Much more important discovery, because it turns out that today, to this very day, we still get our electricity that way. If you trace it all the way back to the power plant, there are magnets, and those magnets are moving constantly, and that motion produces the power that we take for granted. All right? So it really comes back to his ideas. At the end of his life, Faraday was very famous, but he didn't make a lot of money out of his discoveries, obviously. But today, a lot of people, as I say, if you ask them, Albert Einstein, have you heard of Albert Einstein? Most people have heard of him. Not many people have heard of this guy. I think in some ways more important. All right, let's have a look at what he actually discovered. Now, the principle that Faraday discovered was that if you move a magnet toward a coil of wire, that movement will produce an electric current in the coil. In other words, it is the relative motion between a magnet and a coil that produces electricity. Now, we can do a very simple experiment. We can get a permanent magnet and we can just move it in and out of a coil, and we can connect the little current meter to the coil, and we will see that the needle moves back and forth as we move the magnet into the coil. Now, you might think, how on earth did it take people that long to discover that? That sounds really obvious now, doesn't it? Well, you've just got to get the magnet and move it into the coil. But sometimes the most simple things are the hardest things to discover. You know, and it took 20 years of people thinking about this stuff to finally come up with this experiment and show that this was the principle behind producing electricity. Now, that process is called induction. Very important word. Let me just stress this word. This is a word you might hear in other contexts. The word comes from the word induce. Now, if I induce something to happen, what am I doing? I induce you to study physics. What am I doing? I'm encouraging you. The point is that I'm giving some momentum to you to do something. And in the same way, in this process, you are encouraging electricity to flow. You're doing that by moving this magnet. That's really the key. So the word induction means to cause something to happen. All right? You can think of it that way. Cause something to happen. And I'm going to use that word a lot. What does the word electromagnetic mean? Well, you can see by the word, we've combined electrical and magnetic together. And this was another thing that Faraday did that was so earth-shattering. Up until Faraday's work, people thought of magnetism and electricity as separate things. Now, that's very hard for you and I to accept today, because we've grown up in a world where we take for granted that the two are connected. But let me put it this way. Supposing you had never heard anything about physics, wouldn't that be good, huh? Never heard anything about physics? And all you had was a permanent magnet, and I said to you, with that permanent magnet, what is the connection between this permanent magnet and electricity? If you look at a permanent magnet, you can attract another magnet to it. What in a permanent magnet tells you anything about electricity? Nothing, really. You think about it. It's not obvious that magnetism and electricity are connected. Okay, and we take it for granted now, but again, it took quite a lot of work to sort of see that, all right? So we combine the two in that word, electromagnetic. Now, here's a very important point. If you move the coil toward the magnet, notice how here you're moving the magnet toward the coil. It turns out that if you keep the magnet still and you move the coil toward the magnet, the same thing will happen. In other words, there is no difference between moving the magnet toward the coil and moving the coil toward the magnet. All that matters is the relative motion between the two. That's it. Alright? So if you have that relative motion, you're going to get some sort of electricity to flow through. Incidentally, what kind of current is that? If you move the magnet toward, the current goes this way. If you move it away, it goes this way. So the kind of current we've got, obviously, is AC. Alright, so we're going to get AC current. If we want to convert that current to DC, we're going to have to do something to do it, to make the AC into DC. Now, have you noticed that all of the power that's generated in the world today is AC? We don't generate current DC. And you might have wondered why AC and not DC. Well, hopefully now you can see part of the reason. Because AC current naturally comes out of this process, doesn't it? If we're only DC, we're going to have to force that AC to become one direction. Alright? Now, obviously, in the power station, we don't have some guy there going, you know, we'd have to pay them a lot of money, wouldn't we? All right. And also, it turns out that the amount of electricity we get is very small. All right. As we will see in a moment, you need to move that magnet or the coil really quickly to even get a few volts. So we can't do it in that sort of crude way. How do we do it? Well, most of you are probably aware that the motion is caused by burning fossil fuels. That's the main way we do it. We burn fuel. And as a result of burning the fuel, we get motion eventually. So it's not a perfect method, is it? There is a downside to this method. In order to get the movement we need to burn some fuel. And of course, that leads to the greenhouse effect and all that yucky stuff that we don't like. What's the other way we can do it? The other way we can do it is with nuclear power. It doesn't create greenhouse effect, but it has other side effects, as we've seen in the last year or so. Alright, just to emphasize that it's relative motion that matters, have a look at this diagram here. What you've got is a loop of wire, and remember what the X's mean. The X's mean that magnetic field is going into the page. So let's say that I have a magnetic field pointing into the page, and I get a loop of wire, and I pull that loop of wire this way. If I change the area of that loop, then I'm going to change the number of field lines that are going through that area. And we will see that that is the key. If you can change the number of field lines going through a region, you're going to get current. But you've got to change it in some way, all right? If you change the magnetic field, you will get a current. And if you look back here, you can see by moving this north pole toward here, we are going to increase the number of those red field lines that go through that coil. By increasing it, we get some current. If we move the magnet away from the coil, we're going to decrease the number of field lines through the coil. Now, does it matter whether we increase or decrease the field? The answer is no. In other words, the increase or decrease only determines the direction of the current. It doesn't determine how much current. You can either decrease it or increase it. Either one will produce a voltage and a current. Now, one other word that I need to explain that we haven't talked about much so far is this word here, EMF. And the symbol is not an E, it's a Greek letter E, epsilon, and it stands for electromotive force. Now, let me just say something about this word. The first thing is, if you see the word force, what units do you think of straight away? Newtons, right? But it turns out that this is not a force at all, it's a voltage. In other words, by doing this process, we get some volts, and the volts can then act like a battery and we get some current. So why did they call it force? Well, here's another history lesson for you. We've already told you that back in the 18th and 19th centuries, the big hero of physics was Isaac Newton. And all of the physics we've taught you so far has been what we call Newtonian physics. Now, in the Newtonian view of the world, everything can be explained by forces pushing on things, pushes and pulls. But you have a think about this process here. Have a think about what's going on here. Can that process be explained simply by pushing and pulling objects? Not really. There's something going on in the space around the magnet. And when Faraday came out with this idea, people said, "What are you talking about, lines of force? Where are they? I can't see them. Here's my magnet. Where's the lines of force?" And Faraday said, "Well, I don't know. I can't prove it to you, but I think there are some lines of force around the magnet." At first, people kind of laughed at him and said that he was crazy. We now take that idea for granted, right? So, I'm sorry to say that this is a misleading term. The word force should not be used in this context, but you know what physicists are like. They don't like to change their ways. So they called it electromotive force back then, and they still call it electromotive force now, but it's a voltage. Alright, so just a little point of clarification. Alright, let's have a look at one common example of what we're talking about. And this example that we're going to talk about now, before I look at it, can I just point out that it is, again, not a very practical example. The only reason we will go through this is because it helps you understand the concept. This does not happen in the power station, okay? It's a different process, but hopefully you will at least get the idea of what is going on here. Alright, what we have is we have a metal rod, can be made of any conductor, and then around that rod we've got a circuit. Just a loop of wire connecting the circuit. And then in here we're going to put a little light globe. Where's the battery? Where's the battery? Answer is no battery. We don't need a battery anymore because we're going to be the battery. You understand? This process, there's no battery. We're going to be the battery. We're going to provide the energy. Now going through there, once again, we have some magnetic field lines. Okay, and those field lines, in this particular case, are going into the page. Now here's a new word for you that you need to know. The new word is flux. What is flux? Magnetic flux is related to magnetic field. They are related to each other. So what's the difference between magnetic flux and magnetic field? The answer is, we'll make clear in a moment, but for now, can you just assume that magnetic flux is magnetic field lines? That's what I want you to understand. In other words, the more field lines you've got, the more flux you've got. If it helps you, just think of one field line as one flux. It doesn't really work that way. We can't count field lines, right? But if it helps you, that's fine. So how much flux do I have going through this circuit? Well, we don't really need this bit here because what we're going to do now is we're going to move the rod to the right. What's the circuit at time 0? T0 equals 0. How many flux lines have I got going through my circuit according to that diagram? Count them. What's the starting flux through my circuit? No, not 0. Firstly, what's the area of the circuit that I'm looking at? The left area, right? It's this bit here. You see it? This circuit is the starting circuit. I haven't moved it that way yet, so this bit's not here yet. Forget it, right? So 3, 6, 9, right? The symbol for flux is an O with a little line through it. It's a Greek letter phi, not beta, phi. So the initial flux is 9 units. Right? Now then what I'm going to do, I'm going to move the rod to the right until over here, the rod's going to be sitting over here. What's the final flux through my circuit by the time I've moved the rod from here to here? 9 plus 6, which is 15. So the final flux is 15. I changed the flux. And because I changed the flux, Faraday says I'm going to get a current. That means I'm going to get an EMF across here first. I said current, and then I said EMF. What's the relationship between EMF and current? What's the relationship between volts and current? First semester. What's the law that we use to connect V to I? Ohm's law, isn't it? Before we get the current, we're going to get the EMF. So let's look at the EMF first. Now, how am I going to tell whether this is plus and this is minus, or whether this is minus, and this is plus? You are going to use your right-hand rule. Remember from last week your right-hand rule. First question is, are you going to use the second right-hand rule, or are you going to use the first right-hand rule? It's the first one we need here, isn't it? Because we already have a magnetic field. We're not trying to find a magnetic field. We're going to try and find a force. Now, what way am I going to point my thumb? Listen to this really carefully. This is the tricky bit. Last week, what did we tell you your thumb represented? You've forgotten already. It was only last week. What was the thumb in the right-hand rule? No. Last week. No. What's the thumb in the first right-hand rule? The direction of what? No. Last week. Forget this week. What did we tell you last week this was? Current. You've forgotten already. This was current, this was field, and this was force. This was current, wasn't it, last week? If you think about it. But have a look at here. You haven't got any current. You haven't got any current. So what way are you going to point your thumb? You haven't got current. You can't point thumb in the direction of current. Well, think of it this way. This rod has inside it lots of what? Little electrons. And if you move that rod to the right, aren't those electrons going to be moving? Isn't that a current? In a way it is. It's just a different kind of current. The current didn't come from a battery, did it? The current came from you moving the rod. So from now on, when you use your right-hand rule, what's your thumb going to be? Motion, right? You've got to relearn the right-hand rule for this situation. There is no current at the beginning. There's only motion at the beginning. So get your thumb, right, point it this way. You're moving the rod this way. And where are your fingers going to point? Once again, magnetic field lines. And the line out of your palm tells you the direction of positive, careful, these are electrons, right? Positive charge flow toward the up. If protons could flow, what way would they go? They would go up, and that would make this positive, and the electrons would go down, making this negative. You see it? What have we got across the ends of this rod? Before we have the current, we have an EMF. You get a voltmeter, you can connect across here, you'll find some volts. Alright? So, just to repeat, you don't have to relearn the right-hand rule. You can still use the right-hand rule. All you've got to remember is the thumb indicates motion this time, because you're going to start with movement. Fingers are still magnetic field, and the line out of your palm is the conventional current that flows in the rod. Conventional current. Or, if you liked, you could have done that with your left hand, and you would have found the electrons go down to the bottom. Alright. Now, this bit's also a bit tricky. Now that we have a plus and a minus, what kind of field am I going to have between the ends of the rod? Not a magnetic field, an electric field. Alright, an electric field. And the electric field is going to be pointing which way? The electric field always points from positive to negative. So you're going to have an electric field pointing there, which means your electric force is pointing down. And what about the magnetic force? Where's the magnetic force pulling? On positive charges, the magnetic force is pulling the positive charges to the top. Which one of those two is going to be bigger at the beginning? Which one is going to be bigger at the beginning? The electrical or the magnetic? If it was the electrical, they'd never get moving, would they? You see it? Because if the electrical force won, they'd never be able to move up. Turns out that this one's bigger at the start, you see? The reason why the magnetic force is bigger is because I don't have much charge. But if this process continues, what are you going to get? Another positive charge going to move to the top? Another negative charge down here? What's going to happen to this force? It's going to get bigger. This one doesn't change. Eventually, what are you going to have? Eventually, both forces are going to be in equilibrium. And when the two forces are in equilibrium, the process will finish. And that will be your final current. Now, can we get an equation for this? All we need is a formula for that and a formula for that. And you should already know what those formulas are, right? Because you remember everything we did in first semester. Is that right? No? But Fe, remember, the formula was E equals F over Q. So therefore, Fe is QE. What about the magnetic force? What's the formula? F equals BIL. So if this is equal to FB, we get BIL. But hang on, probably better not to use BIL, but QVB, because we're dealing with a single charge. We're looking at just a single charge. What have we got on both sides? We've got a Q here and a Q here, right? And based on that, we can get a formula. But there's one more step. We haven't got voltage here, have we? We want to get EMF into the equation. Does anyone remember a formula that connected electric field to V? Can you remember from first semester a formula we did? Voltage over distance. If you have two parallel plates, V divided by D. In this case, we won't call it D, we'll call it L, because L is the length of the rod. So I just replace E with V over L. V over L equals VB. But we don't use V, we use epsilon. And then what do you get? VBL. There's one thing I have to add. What assumption am I making? The assumption I'm making is that the rod is moving at right angles to the field. What did we tell you last week happens if you move the charges in the direction of the field? If you move the charges in the direction of the magnetic field lines, nothing happens. So we have to put sine theta. That's it, that's the formula. That's your first formula, which should be in the notes. About third or fourth page. Alright, why is this formula so useful? Because it tells you the four things that are going to affect how many volts. If you want to get more voltage from your power generation, you got 4 choices. Now, can anyone tell me out of those 4 which one we can normally change in a power station? If we build a power station, we try to generate electricity, which of these 4 variables can we change? Okay, B, we're limited by how much magnetic field we can make. We can't keep increasing a magnetic field forever. We can generate more powerful magnets, yeah, but we're going to hit a limit. So, you know, this one here, we're limited. L, what are we going to do? We're going to build a magnet that's 4 kilometers long. More L, more V. But then we'll have the whole city will be a power plant. No one will have anywhere to live. That's not very good, is it? So L can't do much about it. Theta can't do much about that either, because the maximum is 90 degrees. So all we're left with is V. So how do we make the thing spin faster? The only way we can make it spin faster is put more fuel in. Put more fuel in, more greenhouse. You see the problem? But hey, don't blame Michael Faraday, right? Michael Faraday is not responsible for the greenhouse effect. Okay? Don't blame him. Okay? Without this theory, we wouldn't have had 200 years of readily accessible electricity and nothing would work. Just to give you an idea, before they came out with this theory, the way that you had to get your electricity, you basically had to go to an electricity provider and they would give you a certain amount of electricity from a generator that you could use for that month. And when that ran out, bad luck. No more electricity. It was a little bit like today when you choose an internet provider. You get a certain amount of download a month or whatever. And once you've run out, oh well, you've run out. Used to be a little bit like that with electricity too. Run out of your electricity, oh well, sorry, buy more. Alright, so first formula that you need there. Alright, now obviously, if you move the rod to the left, then all that will happen is these will start to swap around. In other words, this will become a negative, this will become a positive. So you can change the direction of the EMF by simply moving in the opposite direction. Now, one more thing we need to look at here. I might need to redraw this diagram, it's getting a bit messy. Okay, we said that if you move the rod to the right, you will get an induced current, and the induced current will go toward here. This is an induced current. You understand? That current was induced by us. We made it happen. We caused it to occur just by using your right-hand rule. Is that the end of the story? Well, you think about last week. What did we teach you last week? We taught you that whenever there is a current in a magnetic field, what happens? If you have a current in a magnetic field, what do you get? A force. But remember how we pointed our thumb this way to get that current? What way am I going to have to point my thumb now? Well, I got a current. This current is going to produce a force, isn't it? So now I've got to do it again. You see? I used the right-hand rule to figure out the induced current. Now I get the induced current, I've got to figure out what force is going to be on that induced current. Now can you see what direction that force is going to be? It's going to be that way. What do you notice about that force? The force is opposing what you're trying to do. And you will see that no matter what you try and do, that will happen. And that shouldn't surprise you, because that is the law of what? The law of conservation of energy. Imagine if you got a force in the same direction as you were moving. What would that mean? Supposing you move this to the right, and then you got a force that way as well. That would mean that nature was trying to help you. Wouldn't that be a great universe? Unfortunately, it's not the universe we live in. The universe we live in is one where things always oppose us, right? But this is an opposing force. Very important that you understand that. If you want to keep that rod moving at a constant speed, you are going to have to apply a force yourself that is equal and opposite to that opposing force. And that means you are going to have to apply a force from your hand to keep this moving at constant speed. Otherwise, as soon as you let go, what's going to happen? As soon as you let go, the only force is going to be this one, and the whole thing's just going to come to a stop. So our modern power generation rests on one assumption, and that is that in the power station, 24 hours a day, 7 days a week, those magnets keep turning. And you know how we get when they don't turn, right? We all get very angry. People do not like to have no electricity, and I am no exception. If I have a power blackout, I don't think, oh, don't blame Michael Faraday, it's okay, you know. I think, where's my electricity, you know? And you probably think the same. We sort of assume that it's always going to be there. So can I just make something clear here? In this diagram, you can see the force of the hand basically means you are having to put that force in. But the actual magnetic force is this one here. Now here's another way to think about it. Remember the concept of work. Work is force times distance. And I'm telling you, you're going to need a force here multiplied by that distance, and therefore you are going to have to do work. That's another way to think about it. This light globe lights up. It lights up because of your work. Okay, that's it. You are the energy source. You are the battery. Alright, let's look at one other example of this. Once again, this is not a practical example. It does not happen like this in the real world. This is an example that will hopefully help you to understand the concept. The way they've drawn the diagram up there is like that, but I'd like to just draw it a little bit differently because I think it's a little bit confusing. So if you want to, you can sketch my diagram here, and if you prefer mine, you can use that. If that makes sense to you, that's fine. The main thing here is that this B is out of the page. So what I'm going to do, I'm just going to draw two metal rails. There's the first rail, and then over here another one, and then in between we have our metal rod. And the magnetic field is out of the page. How do I represent out of the page? Just with some dots. So what I'm going to do is just draw some red dots there. That represents magnetic field coming out at you. Okay? This is the rod. What are these things? They're just little rails that touch the rod on either side. They're just slides there. Don't worry about friction. We'll assume there isn't any. Keep it simple. So what we're going to do is just drop the rod. What's going to happen? Okay, if you understood nothing that I just said, you would say the rod will fall at 9.8 meters per second squared. So what? Of course the rod will not fall at 9.8 meters per second squared. Why not? Because as soon as the rod starts to fall, you have motion V in a magnetic field. Can you show me how you're going to use your right hand rule to figure out the induced current? Give me your hand. Show me what you're going to do. Where are you pointing these fingers? That's the first decision. Where's the magnetic field? Out of the page, right? So you've got to go either like that. Looks like I'm doing some rap balance or something. Like this. Where's your thumb going to point? Always the direction of motion. Down, right? So you've got to go either like the up. Right? It's something like that, isn't it? The rod is moving down, the field is out. So the line out of your palm is this way. See it? So the induced current goes there. This becomes positive. This becomes negative. You with me? Okay. Now, that wasn't the end of the story. The next part was, we had to figure out, now that we've got the induced current, what direction is the force? So you must point your thumb in the direction of the induced current. So, point your thumb here, point your fingers out, and the line out of your palm is up. There's your force. What do you notice about the force? The force is opposite to the way it's moving. So what are you going to observe as the rod falls? It's not going to fall at 9.8 as it normally would. What's going to happen is it's going to slow down, isn't it? Because the net force is going to be pointing, eventually, it's up at the beginning. But it depends, it's a tug of war between two forces, isn't it? What two forces are we dealing with? Draw a free body diagram. Gravity and magnetism. So there's FB, and there's weight. Weight, we learned in first semester, is equal to mg. And better not call it W, call it mg. This one, what formula? Last time I used QVB, didn't I? I think we probably shouldn't use QVB this time because we actually have a rod with current going through it. So we're going to use BIL, sine theta. In this case, it's a right angle, isn't it? Because the motion is this way, the field is this way. Okay, now, eventually the rod will reach constant velocity, won't it? So we'll write down here, when equilibrium is reached,